Hi there, and thanks for joining our course on laser physics and watching our lecture regarding the pumping schemes on our first chapter. So essentially what I will be talking about this lecture will be introducing a few pumping schemes, mainly the 2-level, 3-level, and 4-level system, and I will try to unravel you why the 4-level system is the kind of easiest to reach a population inversion and thus a lasing system. So that's the main topic of today or in this lecture. So I will just get started by recapping what we already learned in the previous lecture. So the population inversion, this is a necessary condition for lasing, and what is required is essentially the fact that the electron population in the excited state must be larger than the electron population at the ground state. So here NE is the population of the excited state and NG is the population of the ground state. And of course, when we would have more states than just two, things would be a little bit more complicated in terms of the sub-indices and terminology, but let's get into that later. So, as we learned, a pumping mechanism is really needed to achieve a population inversion, and we need this to try the system out of a thermal equilibrium. So we cannot really realize population inversion in thermal equilibrium as we learned in the previous lecture. So this is schematically showing what we need to have. So essentially what we have is that we need to have some kind of pumping scheme that is really lifting the electrons from the ground state or the state number 1 into the excited state, or sometimes labeled as the state number 2. This terminology with the state numbering makes more sense when we are going into the 3-level and 4-level system. So that's the reason why we have them also labeled like this here on these pictures so far. So we need a strong pumping mechanism. Sometimes it's optical pumping, so we really have another, for example, laser pumping our gain medium, or it could also be electrical currents, as is done in semiconductor lasers. So basically, electrical current is exciting electrons from the valence band into the conduction band, creating a population inversion in a semiconducting system. Here, in 2-level system, what we do have is that we have population inversion, but we cannot really achieve population inversion in a 2-level system, and this is due to the fact that the absorption and the stimulated emission, the competing processes, at best we can have them occurring at equal rates when we have an equality in the populations. So what this means is that the net change of photon flux becomes 0. And this means that we cannot have light amplification. Even in the case of pumping the system very strongly and continuously, the system would only reach an equilibrium, but not really an inversion. And this is the reason why we cannot have population inversion and lasing in a 2-level system. So, in order to enable population inversion and lasing action or oscillation, using this terminology, using the word oscillation, we really must have a more complex system. So essentially, for example, a 3-level system or a 4-level system where we have our atomic or molecular systems consisting of more than just a single or 2 energy levels. So this is the conventional scheme of realizing actually a laser device. And of course, you could instantly try to generalize the approach. Why not 5-level systems and so forth? The key answer here is that because 4-level system is already adequate for describing a conceptual difference from a 3-level system. That is the first complication from a 2-level system that allows lasing action to take place. So that's the motivation here. These are the simplest configurations and they work, so we do not need to consider anything more complicated. So let's look into the 3-level system first. So what do we have here? That's the simplest possible scenario beyond the 2-level system. And in a 3-level system, we have a pumping mechanism, as before, that excites those electrons from the ground state, labeled as G, to an ancillary state or auxiliary state, labeled as A. And this figure hopefully clarifies how the situation is. So we have the ground state here labeled with G or 1, and we are having a pumping mechanism, let it be optical light or electrical currents that are exciting electrons into the auxiliary or ancillary system labeled as A or 3, and then something happens as we will be describing later. So we do pump photons, and the frequency of photons will be nu p. That equals, of course, the energy difference divided by the Planck constant of those two respective states, and these need to be absorbed into the material so that we can really excite the system from the ground state into the angular state of A. And now the magic happens. If the system really goes under a fast non-radiative decay, then we can have a relaxation of electrons from the state A to the upper laser level denoted with E. So that's what's the kind of key ingredient that we require. So we need to have some kind of relaxation of electrons in a controlled manner and a quick manner into this laser level denoted with E, or label 2 here. So that's what's happening. We are now having a situation that we have electrons here, and now we may have lasing between the state 2 and 1, or E and G here. And this is the key here, that we need this kind of fast non-radiative decay from the state 3 to the state 2. So as long as the lifetime between the transition from the state 3 to state 2, labeled with the tau 32, is fast or short compared to the lifetime of tau 2, which denotes the transition or relaxation of the state E into the ground state, then population can start accumulating into the excited state. That's the key here. So let me recap here. We need to have a relatively fast transition between the transition from level 3 to level 2, and then relatively slow transition from the 2 to 1, so that we can really start having accumulation of electron states here. And the terminology I'm using here, tau 3 to these two indices here, are trying to clarify the fact that we are really interested in this transition. In principle, of course, these electrons could also transfer or relax from the state 3 directly into the ground state, and this is what often also happens, of course, but that's not the transition of interest, and we try to specify that we are really interested in this specific relaxation here, and we want to compare this with the lifetime of going from state 2 into state 1, so into the ground state. And here, since we don't have any kind of alternative channels, the only way this state 2 can relax is actually by relaxation into the ground state. So we do not really need to specify what specific relaxation channel we are considering when we are labeling this lifetime here. So that's why we only have 2 here, and here 3, 2. So that's the kind of philosophy between the different index notations. So here we are specifying with 2 indices that we are really looking at the relaxation from state 3 to state 2, and here in terms of state 2 there's really no other mechanisms. There's only one relaxation channel, so it's adequate that we label that with a tau 2. So I hope I clarified that issue. So laser transition occurs between the excited state E and G, the ground state, and that occurs when the frequency fulfills the condition, so that the E2 minus E1 divided by Planck constant is the frequency. And now population inversion between the states E and G becomes possible, and this allows the amplification of light at that frequency of nu naught. So this is what can happen in a 3-level system. And now a crucial ingredient that we should also take into account. So let's look at now the energy difference, and this is also known as the Stokes shift between the angular state A and the excited state E, the laser state. And this is known as the quantum defect. And already in the figure, we were labeling that with a red Q parameter. So this quantum defect Q equals to H Planck constant times nu p, the pump frequency, minus Planck constant times the nu naught. That's the lasing frequency. So we can write this differently in this way. And now we basically have a quantum defect definition. Often this value is given in percents, and in practice this is an extremely important parameter of lasers. And why this is so? Well, if we have a larger quantum defect, basically we will have a faster heating of the gain medium, and ultimately heating of the gain medium is the main limiting factor that limits the power scaling of our laser system. So all gain medium will be heated. All gain medium in practice will be also cooled down, and at some point, technologically, you just cannot cool down the gain medium quick enough or efficiently enough, and it starts cracking down due to the fact that you have temperature gradients present in the gain medium. There are many approaches to try to circumvent this fundamental issue, but that's basically usually the key crucial factor that is limiting the power scaling of a laser system. Another issue caused by the larger quantum defect is also the fact that now we have a reduction in the power efficiency. So basically, like looking at these arrows here, we need a given amount of energy to pump the electrons here, and in a way we are losing energy into the heat accumulation in the lasing gain medium due to this quantum defect here, and this will be the kind of output power here. So the kind of larger this energy difference is, then reduced will be our power efficiency. So that's one issue here. And let me repeat, this is a key ingredient in real laser systems, quantum defect and how it affects heating. Really look at this energy difference. All this energy basically will be dissipated and stored as heat in the gain medium. And this is really detrimental for the behavior of the laser in practice. Okay, so what kind of limitations we have for the 3-level system? It works, you can make a laser, but it's a little bit limited in its capabilities. So we require a relatively high intensity pump to efficiently excite the atoms from the ground state into the auxiliary state. And in addition, we also must have a situation where the ground state will be efficiently depleted so that the population inversion will be sustained. So in a way, these 2 points are connected. We really need a strong pumping condition so that we can deplete the ground state, in addition of having a large enough concentration of electrons at the lasing level E, or E or 2. So these things are the kind of detrimental factors in a 3-level lasing system. But despite this limitation, 3-level systems work, and historically especially they are extremely important. For example, the first Ruby laser was really based on a 3-level scheme. And now we go forward and we want to look into a little bit more complicated system and try to understand what's the kind of limitation in a 3-level system that can be improved seriously by considering a more complicated system. So let's now look into a 4-level system or a quasi 3-level system, which is essentially very similar conceptually to a 4-level system. Okay, so in a 4-level system with a pump frequency of nu p, we have the energy difference coming from the energy difference between the auxiliary state of E3 and the ground state. So this is again the energy difference between the ground state G and the highest energy level 3. So now we are finally getting the figure that helps out the scheme. So now we have 4 energy levels here. We are pumping again from the ground state, and this time we have this auxiliary state denoted with a label 3. And now you start seeing the reasoning why we sometimes use these labels 1, 2, and 3, and sometimes G and E in the kind of denoting the different energy states of the electrons. So now what happens is that we now have the system relaxing from the state 3, again via non-radiative decay, and this is of course usually very fast, to the upper laser level denoted with the ket of T2. And now population inversion can be achieved between the levels of 2 and 1, and we can obtain amplification of incoming flux of light at a frequency of nu E2 minus E1 divided by Planck constant, corresponding to the energy difference between the upper and the lower laser level. So what happens here is that we are pumping, raising electrons into here. Again, non-radiative decay happens. We have electrons at the state 2, and then we may have lasing action here between the state 2 and state 1, and then ultimately these electrons will be relaxing from the state 1 into the ground state. And here's the crucial difference between the 3-level system and a 4-level system that we will be now finally telling to you. So this main advantage when moving into a more complicated system, so moving into a 4-level system and not a 3-level system, is that now once we have electrons at the lower laser level, the system can very rapidly decay by a non-radiative decay again into the ground state. And now what happens in terms of the population dynamics, this lower laser level is basically empty at all times. So basically the population N1 is close to a 0 at all times. And looking at the condition for lasing, we really need population inversion between the lasing level and the level underneath it. So basically this means that the population inversion can be a lot more easily achieved. So basically this condition delta n equals 0, is greater than 0 is almost always satisfied. So this basically means that in a 4-level system, as long as we can efficiently pump electrons into the excited state here, and basically this happens via this process, as long as we can have electrons a kind of decent amount here in the upper laser level, this state basically very quickly decays into the ground state. The population inversion can be extremely easily achieved, and thus lasing can be extremely easily achieved. So this is the main advantage going into a 4-level system, so that we can have efficient amplification of light and lasing action with a seriously reduced requirement for population threshold. So this is the main thing I wanted to talk to you and mention to you during this lecture. I hope you enjoyed, and I hope it makes sense to you, because this is a really kind of starting point to understand how lasers work. So we go from a 2-level system into a 3-level system and into a 4-level system. And now you see the difference between the 3-level and 4-level systems in terms of their kind of criteria for reaching population inversion. So I thank you for your time and patience, and I wish you a good day. Bye-bye.